All right. So, how's everybody's weekend? Everybody watched that train wreck of the Super Bowl yesterday? You didn't miss anything other than Bad Bunny. Bad Bunny crushed it. Everybody else was pretty awful. Even Green Day. I was expecting Green Day to at least make it entertaining, but they took all the political stuff out of their lyrics, which was the point of Green Day. I'm gonna. Anyway. All right, so couple things for this week and next week. Lab is gonna be, this week's lab is gonna be paper-based. It's gonna be practice naming compounds. It's still worth coming to the first 30 minutes or so of lab to make sure that you get all the information, and I'll walk through some of the process for naming these compounds. But basically, once you've done that, and I'll probably record today's anyway, so that you can go back and revisit it if you need to. But it'll be a short lab meeting this week, and then next week we have Monday off. So we don't have any official lab meetings next week. So it'll be a computer-based assignment, where we'll basically, and it's actually not a consolation prize of a lab. It's actually a really good lab that we do even when we don't have like a Monday off. Because it's really good practice for trying to visualize some of these molecules in 3 dimensions. Turns out that actually takes a fair bit of practice. It's for some people it comes relatively easy, but it still takes a little bit of practice, and some people will struggle with it. Oddly enough, this is when it comes to visualizing molecules in 3 dimensions, this is actually one place where people that play video games actually have an advantage. They've done some interesting studies that in chemistry and organic chemistry, specific skills like visualizing things in 3 dimensions. It turns out playing video games where you're used to looking at a 2-dimensional screen and seeing it in 3 dimensions is actually a useful skill when it comes to chemistry. I mean, it's still not gonna, replace actually putting in work and practicing and studying. But that's kind of an interesting correlation that they've seen in chemistry students. There's a lot of interesting lurking variables there too, because there's also both doing well at chemistry classes has traditionally been linked to male students, and not necessarily because male students are any better, but because most classes have traditionally had success linked to being male. Just because of the systematic sexism in our society and culture. And males also tend to play more video games. So there could be a correlation there that means that playing video games doesn't make you better at chemistry, but people that play video games also tend to do better at chemistry classes. Could just be a correlation, not causation. And we gotta be careful about drawing conclusions where there aren't necessarily conclusions, where there's something else happening. And it turns out systemic discrimination is definitely one of those things that can affect some of those studies. That's a random aside though. Lots of good random questions. Somebody asked about, is there other ways to count valence electrons and electron configurations? Absolutely. I teach the way that makes the most sense to me. But there's also, I don't like this method, but there's a way of drawing like a triangle. Like where you basically list out the different orbitals, like 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and so on. And does this look familiar to anybody? Some of you have seen this before. This was not what you were thinking of, Brooke. So this is one way to do it, because if you're trying to remember the order of basically you draw diagonal lines to tell you the order of these, where you say, okay, well, I'm going to start with 1s and then I get to the end here. And then I start here and I draw a diagonal line and I get to the end, and then I do 2p, 3s, and then I do 3p, 4s, 3d, 4p. Then there would be 5s down here. I've seen this before, but it doesn't really seem like it's that much more helpful than just learning how to use the periodic table. If you have already taken a chemistry class where they taught you to do electron configuration this way, that's still valid. Still follows the same rules, makes everything match up nicely. I don't like it because you still have to know how to draw the triangle properly. And at that point, why not just learn how to use the periodic table that's sitting right in front of you? But yeah, there are other ways to do electron configuration, to count valence electrons. You don't necessarily need to write out the electron configuration to get valence electrons, right? Once we get used to doing valence electrons by looking on your periodic table, that's usually faster than actually writing out the electron configuration and counting how many electrons are in the second energy level or something like that. You can, if you're looking at oxygen, you just count from left to right, skipping the d orbital. That works totally fine too. It's basically because the electron configuration information is coded into the shape of the periodic table. You can just basically use the periodic table itself as a shorthand instead of writing out the electron configuration every time. But yeah, there's lots of tricks out there that kind of give you shortcuts to get around some of these things, because I don't like to teach you a shortcut without teaching you why the shortcut works. That's why I tie everything back to orbitals. That's the way that makes the most sense to me. It explains it from the ground up. But if orbitals are really confusing to you and you just want to learn how to valence electrons, like count columns, skipping the d block, things like that, that's totally fine. Probably the other thing though about electron configuration is basically what we're doing in this class is we're not doing the oversimplified, the second energy level has 8 electrons. We're breaking it up into the individual pieces because that's more accurate. And that explains some of the things that we basically have to hand wave away if we just say this many electrons in the third energy level. Breaking it down into third energy level is s orbital, p orbital, d orbital helps explain some of those other issues. Like why is the third energy level stable when it's got 8 electrons sometimes, and sometimes it needs 18 electrons to be stable? We can explain that by bringing in the d orbitals. So part of it is just because I don't like hand waving past stuff. I want you guys to understand that some of the basic principles before we get into, and this is the shortcut. We're going to talk about questions like this a little bit more today, but this was a really good question. Oxygen's most stable charge is -2. So how do peroxides such as H2O2 work? Hydrogen peroxide is a covalent compound, which means basically there's not enough electrons to go around. If there's not enough electrons to go around, oxygen doesn't get to have a -2 charge. And so that's how you get some of these less stable molecules like H2O2. It's basically what happens when there's a shortage of electrons. When you've got too many nonmetals in one place and everything is trying to gain electrons at the same time, it's sort of the electrons get divvied out to make the most atoms happy, or the most unstable atoms get made more stable first. But when you run out of electrons, sometimes you get weirdness like peroxides. And that's also why hydrogen peroxide is so reactive, is because it's not really settling for a -1 charge. It's forced to sit there with a -1 charge until more electrons come around. And that's why if you let hydrogen peroxide interact with living cells, it basically destroys everything because it's trying to give all those electrons to oxygen to make those oxygens more stable. And in doing so, it winds up breaking down all the proteins and bacteria and cell membranes, which is really good for disinfecting cuts the first time. You never want to put hydrogen peroxide on a cut more than once though. You clean it really well, you might disinfect it with hydrogen peroxide. But then if you continuously do that, every time you change the bandage, you actually are going to do more harm than good and cause more scarring. Because every single time all those cells that are trying to heal are gonna get broken down, even if there's no infection. You're breaking down your cells as well as the bacterial cells. So you don't wanna do that more than once. After you disinfect it, you just keep it covered and let it heal on its own, and that'll give you the best outcomes. This is a really interesting thought experiment, a little bit, because it basically brings up that there's two ways color can happen. The way that we talked about in the flame test was we heat things up, when the electrons settle, it gives off a photon, right? That's what's called an additive color model, where you actually are making photons. But that's not actually what happens. If we look at something like that little insulation mountain range on the back that has those different colors, those aren't glowing, right? If we turn off the light, there's no photons coming from those. But those have color to our eye, because when you shine white light that's made up of all of the visible spectrum onto something, the colors that get absorbed get pulled out of the white light. And what we actually see is what's left over. And so that's a subtractive model, and that's what you use in art theory mostly, because most art is not based around things that glow and give off photons. Most art is based on paints and pigments and things like that, and pigments work by subtracting photons, and then our eye perceives what's left. And so you could say that it's still not really the atoms themselves having color, but it's still the orbitals. That it's just that the orbitals are absorbing the light instead of giving off the light. If we took the same color, highlighters are a really good example of this. If you have a highlighter, this highlighter was going to give me a green color, right? If you shine UV light on this, it'll actually glow green. So that's what happens when you wear neon clothes, and you go to a black light party or something like that, and your clothes all glow with those colors. That's actually turning it from being subtractive color to then, if you put the right wavelength of light on it, it turns into additive color. Because the gap in the energy levels is such that when you shine UV light on it, you actually get photons being created. You actually see some of those light being emitted. But then when you turn off the UV light, it just goes back to being a regular subtractive model. So it's basically the way that we perceive color is very fascinating. The way that we process the information it still all comes back to the orbitals, but it can be different depending on whether you're looking at something under white light or if you're actually exciting the electrons.
So when, let's say, that paint absorbs an electron, where does that energy go? Or sorry, a photon, where does that energy go?
So it depends. Usually with most things, if it's going to absorb a photon, usually there's a whole bunch of other energy levels. They're all really close together. So if we have, say, a whole bunch of energy levels that are all pretty close together, they all have some electrons in them. Basically, those all sort of blend together to make what we call a band. So that band has a whole bunch of electrons in it. And then sometimes there's going to be a gap where there's no orbitals. And then up here, you get a whole bunch of orbitals that don't have any electrons in them. Well, when an electron falls through the gap, it's going to give off a photon. But if it's in this band area, if you have an electron that's like way up here in terms of energy, it can basically sort of slowly fall down through all of those different orbitals that are all really close in energy, and it gives off photons, but they're really, really low energy. And those really low energy photons aren't in the visible spectrum, they're more in either the radio wave region or in the IR region. So basically, you generate heat. That's why if you wear a black shirt in full sun, you get more hot than you do if you wear a white shirt, because the white shirt is reflecting most of the photons. But the black shirt is absorbing all those photons and turning all that light energy into heat, basically vibrations of the atoms themselves. When the atoms vibrate more and more, you get more kinetic energy in the atoms, which means higher temperature. It is. All right. More relevant question. What's the easiest way to determine element stability? Orbitals. Answer to everything in this class, if you want to, is always going to be orbitals. Orbitals and protons, basically. The easiest way to determine an element's stability is you look at how close it is to having all full orbitals. The closer it is to having only full orbitals, typically the more unstable it is, because it only needs to make like 1 or 2 small changes to become fully stable. If everything already has full energy levels, then it doesn't really do anything. Like column 18 on the periodic table. Column 18 on the periodic table is called the noble gases. They don't really react. There's a few jokes in there about they're called noble gases because, you know, nobles stiff upper lip, they don't respond to anything. You could also say because they don't do anything, they're called noble gases. The nobles historically in feudal Europe did not really do much hard labor. So take that how you will. But basically they already have full energy levels, so they're already satisfied, so they don't do anything. Something that's close to being a noble gas but not quite there is going to be working really hard to get to that stable configuration. So typically things at the edge of the periodic table are more reactive. Sorry, if we leave off the noble gases because they're boring. Things closer to the edge of the periodic table are going to be more reactive. Things in the middle of the periodic table are typically less reactive because they're not really close to having a full energy level one way or the other. This is a good historical note. How come when electrons are negative? Why is it that when something gains an electron, we say that it's got a negative charge? That sounds backwards. That's because it is backwards. But unfortunately, when they first decided what electrical charges were, it was actually Ben Franklin's fault. Ben Franklin basically did an experiment. They knew that electrical charge existed. They could generate static electricity, but they didn't know that it was made up of tiny particles. So basically, Ben Franklin did an experiment where he used a piece of glass. He took a piece of silk and he rubbed it on glass. And you notice when you do that, you've got an electrical charge. Basically, you generated static electricity. And so he basically he said, well, I'm just going to call this one negative and this one positive. And he guessed wrong. Basically, he didn't know any better. So it's not really his fault, but we can blame him because he's dead. He's not going to protest. But yeah, if he'd said it backwards, I believe, I'm going from memory here, but I believe that the charge left on the glass is what he called positive. But if he'd said the charge left on the glass was negative, then all of our charges would be flipped. And protons would be negative and electrons would be positive, and then it would all make more sense. However, it's not what happened. Interestingly enough, that actually is what antimatter is. Antimatter, if you've ever heard of that, is really just regular matter with the charges flipped. It doesn't exist in our galaxy, at least not in measurable amounts, unless we make it ourselves. But basically, the charges are somewhat determined randomly. All the matter in our galaxy is predominantly regular matter, which means protons are positive and electrons are negative. But in other places in the universe, there's lots of antimatter where the charges are all flipped. Fun stuff. And then last but not least, somebody asked about the tutoring schedule. I finally got access to a link for the tutoring schedule for chemistry. I put the link in the PDF here. It's also available if you go to the LTCC website under resources. There's a link that says tutoring center that has this same information there. Basically, Atticus is one of our chem tutors. Corinne is not listed as a chemistry tutor, but she has taken all of our chemistry classes here. She probably won't thank me if you go and ask for chemistry questions because it's been a few years, but I know she's taken that. Brad's taken all of our chem classes. Oliver actually is close to a master's in chemistry, but he's not listed as a chem tutor. And where's Omar? Omar has taken our chem classes here too. So there's some good options, and those are some of the tutors that are there more often than anybody else. Atticus and Omar are pretty much always there. And they're really good resources, but Brad's there a lot too. Brad's the big guy who's usually wearing either a Padres hat or a Raiders hat. He's taken all of our chem classes too, and he can help you, especially if you have more of the problem solving questions, the math conversion questions. They're all really good resources. I'm sure that there's some more I'm missing in here that have taken chemistry with only their first names. I'm not entirely sure who I'm looking at. I don't know Bethany, but if she's tutoring A and P, she's probably taken chemistry too. So there's options. This information's in the link that's on the PDF of the slides, or just go to the library and ask who's there that can tutor, that can help you out with chemistry. Omar and Atticus are almost always there, and Brad. All right. Let's talk about isotopes. This is the slides that we skipped the other day when we're done with math and decided to do some more conceptual stuff. I told you we weren't going to skip the math. We're going to have to come back to it eventually anyway. But this might answer some questions that a few of you have had on the quizzes about mass numbers on the periodic table. So remember when we were first learning our spreadsheets and we did that practice where we found the final grade for our 5 fictional students? We said that we were making that final grade was a weighted average of the different categories, right? So we said things like, final grade is equal to the weight on tests as a decimal. Let's see if I can actually remember that. I think the test was 30% times the exam plus 50%, so 0.5 times the homework percent plus 0.2 times the quizzes. We talked about it being a weighted average, right? And basically, if you have a bunch of things and you want to find the average of them, if all of your data points are worth the same, then basically what you do is you make this weight that's in front of each of those values is the same number. If we were just finding the average of 3 data points, let's say we had 6, 5, and 8, and we wanted to find the average of those, how would we do it?
Are you just saying to do 1 times 6 plus 1 times 5?
Not quite. How do we, if we're finding the mean of these, just normally, don't overthink it. If I just said, what's the average? Add them up, divide by 3. That's the simplest way to think about it, and that's the simplest way to put it into your calculator, but that's actually not what's happening when you take an average. When you take an average of 3 data points, if we're gonna value all 3 of these data points the same, we're basically gonna say, okay, I'm gonna take this first value and I'm gonna multiply by 1/3. I'm gonna take this second value and I'm gonna multiply by 1/3. And I'm gonna take this third value and multiply by 1/3. And then I'm gonna add the pieces up. So finding an average is similar to what we're doing here with the weighted average. So what we're doing is we're not saying that all of these data points are worth the same. We're making some of them worth more than others. So it's still finding an average. It's just instead of 1/3 times 6 plus 1/3 times 5 plus 1/3 times 8. If it's a weighted average, we're just taking these numbers in front and we're tweaking them based on how important they are. And so for our final exam, we can set those numbers kind of arbitrarily. I just pick some numbers, right? And say, okay, homework is worth 50%. Isotopes and mass numbers on the periodic table are still weighted averages. It's just that instead of being weighted arbitrarily or being weighted so that they're all worth the same, they're weighted based on how likely they are to be found on Earth. So basically, the weights that we're going to use for atomic mass we're still gonna do the same thing. We're gonna take the mass of each of these and multiply them by a weight, but the weight is based on the probability that if you grabbed an atom at random, it's this specific isotope. So for carbon, carbon's got a mass of 12.011 AMU. 99% of the carbon atoms on Earth are carbon 12. But 1% of them are carbon 13. If you grab a carbon atom at random, there's a 99% chance it's carbon 12. But 1 out of every 100 is carbon 13. So if we want to know what the average weight is of all of them, we have to basically take those numbers and say, okay, well, there's a 99% chance, remember we're gonna do it as a decimal, that I grabbed carbon 12. There's a 1% chance that I grabbed carbon 13. You take 0.99 times 12 and 0.01 times 13, and you add those numbers up, it gives you something really close to 12.011. It won't be exactly the same because I didn't put enough sig figs on this, but it's going to be something really close to 12.01. Actually, I think with these numbers, it will come out to be exactly 12.01. So that's all of these atomic masses are, is basically you take the pieces that you might have and you multiply those pieces by the probability of finding those specific isotopes. And we write that like this. This is a really scary mathematical looking way of doing that. It's got a big Greek letter and a little Greek letter that looks kind of like an X, but it's not an X. It's got subscripts. This is just the mathematical way of saying you're going to add up all of the pieces, where each of the pieces where this Greek letter chi represents that probability. It's also called natural abundance or mole fraction. And it's basically the percentage expressed as a decimal of finding those specific isotopes. Right, and so if you're doing this in handwriting, you're trying to differentiate your chi from your x. Do a little curvy line like a cursive X going one way, and it's almost like a cursive X. And then this subscript here, clean this up a little bit. The subscript just means for all of the pieces. So if there are 3 possibilities for your isotopes, you're going to have 3 of these options. The way that I would write this out for carbon, you can say the atomic mass for carbon if we know that there's only 2 pieces for carbon, it's the mole fraction of carbon 12 times the mass of carbon 12 plus the mole fraction of carbon 13 times the mass of 13. I don't know why I dotted that 1 there. Right. So for however many isotopes you have, you're going to have that many sort of chunks here. Just like for our final grades, however many categories we had all those pieces. We had that many pieces, right? But what's not going to change is that all of your percent of your natural abundances or your mole fractions are always going to add up to 1. Because your total probability has to add up to 1. Just like percentages have to add up to 100, right? All right, let's do a practice with that. This is also another relevant question that somebody asked about the periodic table. Why do some of the mass numbers have brackets? If you check on the periodic table. Of course, they're just, I think on this version, they're parentheses. Basically, those are elements that don't have, that don't occur naturally on Earth. Or at least haven't since we've been looking. And because they don't occur naturally on Earth, we don't have a natural abundance for them. So basically, those elements that don't occur naturally on Earth, we just put the most stable isotope in brackets. So those are the ones, the isotopes that last the longest. So basically, it just means that those are the synthetic elements, and we're not going to have this weighted average situation because they're all breaking down constantly. Which also reminds me one more thing. Somebody caught an error on my periodic table on lawrencium. Lawrencium is, I cannot find lawrencium right now.
It's one of these.
Thank you. Lawrencium, I have listed as LW because for several decades it was LW. Then they decided that that the original research group that made lawrencium actually didn't make lawrencium. They didn't do a good enough job proving that it was lawrencium. And a different group several decades later actually finished the job and demonstrated it. And so they actually went back and changed it to reflect that this new research group actually got credit for it. And so the way that they did that, they couldn't change it from being lawrencium at that point because it had already been on periodic tables for several decades. So they just changed the symbol from being LW to LR. And wherever I pulled this data from when I originally made this had not updated it. And I missed that. So lawrencium is LR, not LW. I don't plan on asking you any questions about lawrencium in the future necessarily, so it shouldn't be an issue. I don't think it was on the quiz last week either. Just a incidental correction. Apologies. Turns out science needs to be adjusted sometimes. All right. Let's do an example for these atomic masses. So chlorine is a really common example because chlorine has two isotopes that both occur in significant amounts on Earth. So chlorine 35 and chlorine 37 both occur in close to a 3-to-1 ratio. So there's a 76% chance that if you grab a chlorine atom at random, it's going to be chlorine 35. But there's a 1 in 4 chance, roughly, grab an atom at random, it's chlorine 37. So that's why when you look at the periodic table, chlorine's atomic mass is not close to a whole number. Because it's going to be in between these two isotopes that both happen in significant amounts. Most of the elements on the periodic table that you see where their mass is really close to a whole number, usually that means there's really only one isotope that occurs in significant amounts. The other ones occur in like 1% or less of the time. But there's a few of them where we have significant amounts of both isotopes. So with this in mind, if we know what the two mole fractions are, and we know what the two masses are, what's the overall atomic mass for chlorine? So you take the mole fraction of each one times the corresponding mass, and you just add the pieces together. Sorry.
Since
I erased the 6 to correct it, and then I rewrote 6. Right, so you take the pieces, you multiply them by the probability of those pieces. So that's gonna be 0.76 times 34.9689 plus 24% times 36.9, etc., 9659. What do we get for a number?
5, 8.
Yeah, technically, I needed to give you more decimals on your mole fractions if we're actually tracking sig figs here, because otherwise we multiply and then you have to round it to only 2 sig figs. So we wind up just getting like 35 back, I think, if we do that. Which is why if you actually look up these mole fractions, you can find all this information from Wikipedia, like I've shown you before, right? This page might make more sense. Actually, we'll do chlorine, since we're talking about chlorine. Ignore AI overview. There's more sig figs, and if you come down here, there's even more, but chlorine 35, 75.8%. Chlorine 37, 24.2%. You come down here and look at chlorine 35 and 37, we get really actually only gives us 3 sig figs down here too. Usually there's more sig figs, so there must be some uncertainty with that. They haven't measured it with more detail than that. Which in this day and age, if there's not more sig figs, then that usually means that there's some specific reason that's preventing them from getting a more accurate number. And it could be something like the isotopic distribution changes just based on where you are on Earth. Or even like, depth of the Earth's crust. Further in you go, might get more of the heavier isotopes. So this might be the best isotopic ratios that we could get based on chlorine's unique properties. Right, so there's another word problem we can look at for this that maybe we'll start with this for practice on Wednesday. We're going to go through it right now, but you can check it on the PDF of the slides. Here's another example where you can have different isotopic ratios, different mole fractions. Anytime you hear of something being enriched can mean a lot of things, but enriched when we're talking about specific isotopes means that they concentrated certain isotopes for some specific reason. So, for instance, lithium gets used in hydrogen bombs. So, but you want one specific isotope of lithium. You don't want just random lithium. You want lithium, I believe lithium 7. No, lithium 6. Lithium 7 is going to be the military application. So you can actually get different isotopic ratios depending on where you're getting your stuff or what it's been used for in the past. So when you hear about enriching uranium, that's what it's talking about, is trying to make it so it's power plant grade uranium by separating out the less useful isotopes. It's really fascinating the way you enrich uranium. So you basically just get a centrifuge that spins at like several thousand times the force of Earth's gravity. If you turns out if you spin things really fast, you can actually get these isotopes to separate based on mass. So the heavier ones go more towards the bottom and the lighter ones stay more towards the top. But you have to go really fast to do that. You can't just use the centrifuges we have in the bio department here. Build an entire plant just dedicated to that. All right, let's go back and talk about ions more. So if we know, we brought up the idea of ionic compounds when we finished lab or we finished class on Wednesday, right? It was, what was the general gist of making these ionic compounds? How do we decide how many of each compound? If I say that sodium chloride is NaCl, how do I know it's not NaCl2? Does anybody remember what we did with that?
One metal to one non-metal.
It's gonna, so these ionic compounds are gonna be one metal to one non-metal, but we can still have different numbers of the non-metal. So we're not gonna have like one sodium, one chlorine, and one iodine all together. So that's what you mean by one metal and one non-metal. But how do we know it's one chlorine to one sodium instead of two chlorines to one sodium? But
They're bound together, it's not loose chlorine.
it's not loose chlorine and loose sodium. So what binds them together? You're answering the questions correctly. I'm just gonna follow the line of thinking there. What makes them stick together?
Just the lack, the electron configuration of them.
Say that louder.
The charge of the
charge of each of them. What's the charge on a stable sodium ion?
+1.
+1, it's in column 1, right? So it has one electron to give away, becomes stable. Which means sodium ions are most stable when they're a +1 charge. What about chlorine? Where does chlorine fit on the periodic table? How many electrons does it need to gain or lose?
Well, gain one.
Gain 1, which gives it the -1 charge. So why do they stick together? Because opposite charges attract. Ionic compounds stick together because positive charges and negative charges naturally stick together. They're naturally drawn together. That's just one of the fundamental rules of our universe. For the magnetic force is caused by opposite charges being attracted to each other. So how do we know it's one chlorine, one sodium? Instead of this ratio.
More stable.
Yes. It's a bit of a non-answer though, because it doesn't explain why it's more stable this way than that way.
It completes a valence shell.
Completes a valence shell. If we're gonna have two chlorines and one sodium, sodium needs to lose one electron and each chlorine needs to gain one electron. Well, if the sodium has one electron to give and the chlorine needs one electron, where would the second electron come from? If basically we need the charges to add up to 0, because otherwise we're saying we made some electron out of nowhere. The charges have to add up to 0 because otherwise this chlorine got an electron that the sodium didn't give it. Right? You need to still account, you need to have a balanced number of electrons from both sides. We can't make matter out of nothing yet. So the practical result of that is that when we write these ionic compounds, we write the formulas for these ionic compounds, we need the charges to add up to 0. So this one can't be true because you got +1 and 2 -1s. That adds up to -1. That doesn't add up to 0, so it's not a stable ionic compound. So let's practice that. We did these ones the other day. So I'm just gonna make some up. We didn't do the last one. What's the ratio of potassium and sulfur we need to get the charges to add up to 0? What's the charge on a potassium ion? +1, because it's in column 1 of the periodic table, right? 1 electron in its valence shell, it wants to give it away. What's the charge on a sulfur when it's stable? -2. It needs to gain 2 electrons to be stable. So how many of each of these do we need so that they add up to 0?
2 potassiums to 1 sulfur.
2 potassiums to 1 sulfur. So +1 and a +1 and a -2 all adds up to 0. And the way we're gonna write that is with subscripts. Anytime we want to talk about how many of each atom we have, we use a subscript after that element. So K2S is the formula that we get for the compound that forms between potassium and sulfur. Right, and what this is saying is that it takes 2 potassiums for every 1 sulfide to add up to a charge of 0. So being able to look at the periodic table and and figure out what the charges on the ions are going to be turns out to be pretty useful because it's going to give us a way to get to these formulas. Let's do another one. Let's do aluminum and oxygen. What's the charge on an oxygen ion? -2. What's the charge on aluminum? This is the one we're gonna have to think about, right? Look at your periodic table. How many valence electrons does aluminum have when it's neutral? Right over here, so 1, 2, 3 valence electrons. And it's a metal, so it's trying to give those electrons away. So aluminum is gonna be a +3 when it's an ion. Cool. We're halfway there. Now, how do we get them to add up to 0?
2, 3.
It's gonna be tricky because one's an odd number and one's an even number, right? So this is like finding the lowest common multiple. If you think back to your math classes, the lowest common multiple of these is gonna be 6, right? So we need enough aluminums to get to +6, and we need enough oxygens to get to -6. So 2 3 pluses and 3 2 minuses is going to give us an overall charge of 0. So the formula for this compound can be 2 aluminums to 3 oxides.
When you're writing it out, does it matter what order you put the elements in?
It does. You're going to put the metal first, followed by the non-metal. Basically, the closer something is to fluorine on the periodic table, the closer to the end of the compound it goes. So we're going to get into other cases where we have 2 non-metals reacting together, and the order still matters. Basically, whatever's closest to fluorine goes last. And it also affects the way we're gonna name these things. So Al2O3 is fine for a formula. If we wanna say the name of this compound though, that's not the name. The name is gonna be based on what the ions are. Since we know aluminum is always a +3 charge, and we know oxygen, when it gets a negative, is always gonna be -2. All we really have to say is aluminum oxide. So the way we name these ionic compounds is we just say the names of the ions. Aluminum. And then remember what I mentioned this last Monday, I think, but I'll reiterate now. Anytime something gains electrons, we drop the ending and we put I. So it's not oxygen, it turns into oxide. The name of this compound is just aluminum oxide. And the formula of this compound is Al2O3. Turns out aluminum oxide is actually a fairly significant compound. Not only is it what forms on the outside of aluminum cans, you can't really see it because it only forms a layer that's a couple atoms thick. But aluminum oxide as a crystal actually is the structure of both sapphires and rubies. Are both aluminum oxide, just with different other there's a few other metals included in there that kind of make it impure. Pure aluminum oxide is like glass, it's perfectly clear. And crystalline. But if you add a little bit of impurity here and there, you get a bunch of different sorts of gemstones. Kind of fun. Turns out almost all geology is silicon and oxygen, with occasionally aluminum and oxygen. All right. So let's do. There's some more practice here. This is just more practice predicting the charge, but I think we're pretty good at that now, but we can do these pretty quickly. What's the charge on the sodium ion? +1. What's the charge on the chloride? Chloride, I went the other way. -1. Magnesium +2. Oxide -2. If we were going to make a compound out of magnesium and chloride, how many of each one do we need? What's the formula for magnesium and chloride? We've got a +2 and a -1. Anytime you have a -1, it makes it pretty easy, right? You just add enough of these so that it adds up to the other charge. So magnesium chloride is MgCl2. Sodium and nitride, what's the formula going to be?
3 sodium.
3 sodiums for every 1 nitride, right? All right, so those are just the answers there. So when we're naming, here's going to be our rules for naming these things. I already said it once, we're going over it again because I want to cement this in here. We're doing a whole lab. It's just pages of practice with naming things. You get the gentle version, it's only 3 pages long. When you take Gen Chem, you'll get the packet that's 14 pages long, that's just practice naming things. Because we want to get, this is learning in foreign language basically. So there's no better way than repetition for getting these rules in your head, right? So anytime the last ion that we have written, anything with a negative charge is called an anion. And anions always have the last syllable of their name replaced by I. So oxygen becomes oxide, nitrogen becomes nitride, phosphorus becomes phosphide, etc. The easy way to remember that an anion is negative. It's not where the name actually originally comes from, but the easy way to remember it is that it's anion stands for a negative ion. It actually comes from the same root as anode and cathode. An anode is negative and a cathode is positive. So it actually comes from before we knew, back from the Ben Franklin days, before we knew what electrons actually were, they knew how to make a positive charge and a negative charge in a battery. So when they eventually figured out what was going on, they used the same root. So a negative ion is always going to be anion. So if anode led to anion, what's a positive ion called? Opposite of an anion is a cathode. Sorry, opposite of an anode is a cathode. A cation. That's positive. Actually, the way that I was taught was just T looks like a positive sign, looks like a plus symbol. Cats are positive because they have paws. That works too. Alright, so cations are positive, anions are negative. When we're saying the name of these ionic compounds, we just say the names of the ions. Because if we know what the ions are, we know what the charges are, we know what the formula is too. So we don't need to specify that what the exact ratio is. And so if we're talking about aluminum chloride, we don't need to say it's aluminum oxide. We don't need to say dialuminum trioxide. That would be redundant. If you know it's an aluminum ion and an oxide, you know that it has to be in this ratio. Right? So we don't overemphasize, we don't use those mono, di, tri, tetra prefixes yet. Those only get used later on for other types of compounds. For ionic compounds, we just say the name of the ions. And we trust that everybody knows how to read the periodic table and figure out the charges. There are some irregulars with the whole like drop the last syllable and turn it into an I. Technically, you're dropping like the last two syllables of oxygen to turn into oxide, but I think everybody's heard the term oxide. Most of these, if I said oxygide, that doesn't sound like a word you've ever heard before, right? But oxide sounds familiar. I'm gonna be too picky about spelling, as long as you remember, turn it into an I. So here's some examples. RBI. What's the name of that compound? Rubidium. Iodide. How about BASE? Barium selenide. Barium's in column 2, so it's going to have a +2 charge. Selenium's in column 16, so it's going to have a -2 charge. So it takes one of each of them to balance everything out. We don't need to say how many of each of them there are. We can just say barium selenide. How about MgBr2? Magnesium bromide. And so don't overthink it with these ionic compounds. You just say the names of the ions. I guarantee you on the final exam, somebody's gonna write magnesium dibromide. It's normal, it happens, because the next system of naming, the next type of compounds we're gonna talk about, we do use those prefixes. So being able to tell the difference between an ionic compound and a molecular compound, or what we call a covalent compound, winds up being important because that tells you how to name it. All right, let's do this slide. This is the almost the last piece of the ionic naming. So what do we do when we don't know the exact charge? And remember, we ended the other day by saying that, okay, well, these two columns, we always know those metals are +1 and +2. And these 6 that I boxed over here, we always know those charges. All the rest of the metals, which in our line goes, our stair-step line between metals and non-metals, is right here. So everything that's not in the first 2 columns, or those 6, has multiple possible charges. If it has multiple possible charges, our rules for naming don't change. We still just say the name of the cation, then the name of the anion. But we have to specify which cation we're talking about. If copper, for instance, can be +1 or +2, if we're talking about copper oxide, we need to specify which copper ion. And we do that by just tagging Roman numerals on the end of the name. Cu1+, the name for that compound, for that ion, is copper-1 ion. If it has a +2 charge, it's copper-2. So when we're saying the names of these compounds, if I said copper-1 oxide, then that's the compound that we make when copper-1 reacts with oxide with a -2. So what's the formula for copper-1 oxide? How many copper-1s do I need to balance out an oxide? 2 coppers to every 1 oxide, right? So Cu2O. Versus if it was copper-2 oxide, copper-2 oxide would be, here's our copper-2 ion. Now we just need them in a 1-to-1 ratio, right? So it still follows our same rules, still say the name of each ion. It's just sometimes with the D block and the F block in particular, we need to be specific which metal ion. Right, and so the old school way of naming these, you actually had to memorize the charges and which one. So we would say that the more positive charge was cupric ion versus cuprous ion. And you just had to memorize that cupric was a +2 and cuprous was a +1. And that was different for all of these. And I don't even know what you did for all the ones that had more than 2 possibilities. So we've gotten rid of that entirely. Roman numerals are still a little confusing, especially once you get to 4 and beyond. But it's way better than having to memorize the charges. At least this way we don't have to memorize the possible charges. If I say ferric chloride, you don't have to go look up what ferric ion is. You can just say iron 3 chloride instead. All right, and so for those ones, like if there was a chromium with a plus, see chromium with a +4, technically that'd be Cr4+. The name would be chromium 4 written like that. you don't know your Roman numerals that well, and you're worried about it, especially on a test, just write regular Arabic numerals. Just write 4. If you do that, I'm not gonna mark you down. It's not technically correct, but I'm not in this class or in this business to teach people how Roman numerals work. I don't like Roman numerals. There's no reason to use them other than IUPAC told us we're supposed to use them. This still communicates the same thing. Okay? So, and on the test, if you try to use the Roman numerals and you get them wrong, I have to mark you wrong. So if you're not sure about how to do Roman numerals 6 versus 4, etc., don't try on the test. Because I don't want to mark you down for getting the right answer but not knowing how to write 6 in Roman numerals. And so when in doubt, use the Arabic numerals. All right, let's take our break. 10 minutes, let's come back at 11:30. And we'll do some practice. Yeah, no. So copper, normally the way we would write copper, we say, oh, it's got 2 valence electrons, so we give up those 2, right?
Right.
But it's, so that would be, that's how you get copper 2. Right. But the other option is if you took one of these electrons and you put it in the d orbital, you get a full d orbital. And then you only have 1 electron to give. And that can happen naturally. Basically, it's similar to that question about the peroxides earlier where I said, well, it depends on how many electrons are around.
Yeah.
You do the same thing, you put copper in different conditions, you get different oxides.
That's interesting.
It is.
Alright, thank you.
That's why if you look at copper oxide, like if you look at a copper like roof oxidizing,
Yeah.
it's like a mixture of blue and green. Copper 2 is blue, but copper 1 is green.
Interesting. Alright, cool.
Actually, I think I have those backwards, but you get the point.
Yeah.
Hey, what up?
Yeah, extra chart.
No problem.
See. Talk about this. I think just in the same question. I think he is. Oh, yeah. But it's last. He said it takes like, it was really boring. It takes longer if we have to read their unless it's a place, some busy great products like. Yeah. But if you buy acres. It's great for those. It's fun. I just do very simple, different. And like, it's just like no one there. No, probably like that. Very good, like just like that. Business, but so yeah, it's not going to it's just like, right, cause like, it's just showing like just like robots, like everything. Lab and right. It's a first of all. Yeah. It takes. There's a part of it that's like special brand. And then I was like, you had to say, oh, yeah, it's like for earlier man for speech, right? But that's the well, yeah. I'm really up to one, but I remember doing it. I was in high school. I remember doing it. Sometimes for excited with in my country, they have a very kind of open well, what's up? Yeah. I'm so excited. I love the director. Yes, so this right, all the charges including shooting hearings. The student plus the only student. Much further. We have 2 cycle years and the lecture ones first. Yeah, that's right. No, she didn't transfer. Why are you so saying? already took some just by some ease. Is it 200 points? Because the lecturers, you like that, that's practicing. Practice stuff like that. You, if you don't do like the last thing. Basically, you look at lots, yeah. You should know this, the hardest equation that anyone's ever seen. That was a good pricing. I'm gonna start going to. He actually. On sketch. And trying to. Plot me. Yeah, how was it?
All right, so as everybody's coming back in here, let's work on these practice problems. If I give you the formula, you give me the name. If I give you the name, you give me the formula. So you were gonna do your, for the rest, would be different? Yes. Because everyone was when you left. Because you actually. When you finish, you will go. Give me the other. People will see it. That means. Alright, so if you've got the formula and you're trying to get the name. Work backwards from the charges that you do know. Figure out the charge on the metal. So we know that chloride is -1. If there's 3 of them, that means that the chromium has to be a +3. That means it's chromium-3 chloride. So something that's going to trip people up. You have to remember that the 3 in the name is talking about the charge on the chromium, not how many you have. Right, if I say Cl3, then the 3 is talking about how many I have, because I'm saying the formula. If I'm saying the name, I'm talking about the charge on the ion. Right, so we have to be careful when we're saying names versus formulas and not mix them up. Right, saying the formula always means you're saying every letter of the formula. Saying the name means you're actually saying the words. It's easy to mix those up. So chromium-3 chloride, the 3 is not talking about how many chlorides or how many coppers. 3 is just talking about the charge on the chromium. So same deal here. We know that iodide is a -1 charge, and there's 1 iodide for every 1 copper. So we know that the charge on the copper also has to be 1. So that means it's copper 1 iodide. And how about strontium sulfide? Do we need a number on that one? They're equal. But even more importantly, strontium is in column 2 of the periodic table, right? Which means it doesn't have a variable charge. When strontium is an ion, it's always a +2. If it's always a +2, I don't need to say strontium 2 sulfide. If I just say strontium sulfide, that implies it's a +2. Because there's only 1 possible charge for a strontium ion. Right, so we only use the Roman numerals when we're not sure what the charge is. When looking at the periodic table doesn't give us enough information to tell what the charge is. So how about Mn3N2? What's the charge on the nitride? -3. So 2 nitrides would add up to a total of -6. So the charge on each manganese has to be +2. Manganese 2 nitride. Aren't you glad you memorized all these atomic symbols and names last week so that we don't have to be second guessing ourselves on them? Part of the reason that I force you to memorize them is so that this part is less painful. Not saying painless, because this is still not super fun. But it's better because at least we know Mn means manganese. How about TiO2? What's the charge on each oxide? Oxide's gonna be -2. And there's 2 of them. So what's the charge on the titanium? Somebody said it. 4. We need, if each oxygen is 2- and there's 2 of them, that's a total of -4. Which means the titanium has to add up to +4. Titanium. Or oxide. All right. Questions so far? I'm gonna clear these ones so I have room to do the silver one. We still know it's an oxide. We know it's silver. What's the charge on the silver? Positive one. Do we need a Roman numeral for silver?
Yes.
So this is one of the reasons I ask. Silver, when it's a stable ion, is always gonna be +1. Because it's in those six from. It's like, remember, silver is always +1. Zinc and cadmium are always +2. Aluminum, gallium, and indium are always +3. So for those six, we don't need a Roman numeral. But if you're ever unsure on test, for instance, Greg, I think silver is one of those ones where we always know the charge, but I'm not quite sure. It's better to be redundant than it is to leave it off when you need it. And so putting the Roman numerals when you don't need them is a -1/4 point. Not writing the Roman numerals when you do need them would be a bigger deduction, would be like -0.5 point. So when in doubt, include the Roman numerals. But in an ideal world, you would remember that those six don't get Roman numerals and you would leave it off. So the actual name for this compound is just silver oxide. How about going the other direction? If you know the name, can we get to the formula? What's the charge on an oxide? -2. What's the charge on iron 3? That's why it's iron 3. So what's the formula going to be? How many of each do we need?
Irons. Oxygen.
2 irons to 3 oxygens. +6 cancels out the -6, so. Fe2O3. Better known as rust. All right, how about nickel 2 chloride? If you're unsure, start by writing out the ions. Nickel's got a +2, chloride's got a -1. We've got to have 2 chlorides for every 1 nickel. Right, so it builds on the concepts we've already been talking about, but it's not that tricky. If you understood charges and valence electrons, this is sort of a kind of a natural extension of that. If you're still struggling with valence electrons, this probably all seems really dense and confusing and hard to wrap your head around, and that's okay, because we'll get you there. It all comes back to the charges. Make the charges add up to 0. How about cadmium telluride? Where's cadmium on the periodic table? 48, right underneath zinc. Which always has a charge of +2. So Cv +2. Where's tellurium? 52. So what's the charge on tellurium gonna be? -2. They're the same charge, they're just gonna add up to 0, right? One of each. So cadmium telluride is just gonna be. Telluride seems like it can't be the right name. Because. Has anybody heard of the word telluride used in everyday life? Where?
I just recognize it. Same.
Maybe it's because I went to grad school in Colorado, but it's a ski town in Colorado. Telluride is on the Front Range, west of Fort Collins. So it seems weird. I believe that the town was named after the compound, not the other way around. Maybe there was an early mining camp there, or the way towns are named in the US is really weird. That everything goes through phases. There was a phase where things were named after minerals. Like Galena, south of Reno, Galena High School. Galena as a compound is a lead ore. So it could just be that the town was named Telluride just because it was a cool sounding mineral name. Couldn't tell you, I don't know the history that well, but that is actually the proper way to turn tellurium into a negative charge, is Telluride. Zinc oxide. ZNO. Zinc is always a +2, oxide's always a -2. So we need one of each. Watch your capitalization, right? With these atomic symbols, we want to be careful with that.
This is titanium 6, right? That's, yeah, you know what I'm saying?
So that would be titanium 4. You probably mix up your Roman numerals. Oxide's -2. And there's 2 of them, so it's gotta be titanium with a +4.
Oh, wait, you're working backwards.
With these transition metals, yeah, because for the most part, you're gonna know the charge of whatever the anion is with more certainty. So you get that one first and then do your cation. If you know, if it's something like zinc, then it doesn't matter which order you work in, because zinc's always +2. All right. Let's talk about those cases where there's not enough electrons to go around. If you've got a system that's entirely made up of non-metals, remember our definition of a non-metal was it was something that's trying to gain electrons to be more stable. If you've only got non-metals around, then they're all trying to gain electrons at the same time. They're all trying to gain electrons, there's not enough electrons to go around, we need some other way to make these elements more stable. And so it turns out the way we can do that is by forming what are called covalent bonds. Right, and so they're called covalent bonds because remember that all of our stability is based on how do we get to full valence shell. Right? If we don't have enough electrons to go around, then we can still fill the valences if we can get these atoms to share electrons. So the word covalent, I'm a little bit embarrassed to say that it took me like 10 years of taking chemistry classes before I realized this. The word covalent literally comes from in both valences at once, covalent. Right, so, and that's exactly what happens. When you get these atoms close enough so that their valence shells can overlap, electrons can be in both valence shells simultaneously. Which means that we basically get to double count electrons. Because they count towards filling up the first atom's valence and they count towards filling up the second atom's valence. Alright, and what that looks like in terms of energy, and I'm not gonna ask you to redraw this graph, but basically the reason this happens naturally, this is not like the atoms get together and decide, oh, let's be roommates so we can, split the rent or something like that. This is entirely just a natural process that happens because if you have two atoms with incomplete valences that are separated by a great distance, they're naturally gonna be drawn towards each other. Because if you look at this graph is energy is on the y-axis and the distance between the atoms is on the x-axis. When you get them really, really far away, there's basically the energy is at zero, but there's a natural force. It's a little bit like if you put a marble on a very, very shallow slope. If you picture putting a marble right here, it's gonna roll really, really slowly at first, and then it's gonna pick up speed, right? And it's gonna wind up sitting in this well at the bottom. That's basically what happens with these atoms. They're really, really far away, but then there's still a small attractive force, just like that marble on a shallow slope, and they start getting drawn closer and closer together until both of their orbitals can overlap. When the orbitals can overlap, they can both be satisfied at the same time. So the simplest example is just two hydrogen atoms. Hydrogen only has one electron, right? But it only needs to gain one electron to have a full valence because it's in that first energy level. So when you have two hydrogen atoms, they're naturally going to pull towards each other until you get this overlap where you've got two electrons sort of sitting in between the two nuclei. And that happens when you get to this specific distance, 74, this is in picometers, it's 74 picometers apart, these two atoms are satisfied. Because both of them have two electrons in their valence shell. Even though there's only a total of two electrons in that system, they both get to count both electrons. And so, how come they don't get any closer? They're kind of, when they overlap like this, you kind of get this like little cloud where there's a lot of electron density. How come they don't get any closer than that? It seems like their orbitals could overlap even more if we got these atoms even closer.
Because the protons are pushing against each other.
Yeah, we have to remember that these nuclei are positively charged. So the electrons are pulling them together so that everything can have a full valence, but the nuclei, that are full of protons are going to push each other away. And there's sort of there's a equilibrium that happens where the nuclei are pushing each other away just as strongly as the electrons are pulling everything close. And so you get a net distance where you're likely to find these hydrogen atoms are going to be roughly 74 picometers apart. I say roughly because it is a measured number and it's actually not constant. If you go back to our marble analogy, the marble rolls down in here and sits here. Is it just going to, when it rolls down, is it going to get to the bottom and just stop? No, what's going to happen? It's going to do that, right? So basically this 74 picometers is the average distance between the two, but when you have two atoms that are linked by a covalent bond like this, they actually behave more like there's a spring attaching them than like a toothpick. Did anybody have to build atom or molecules with toothpicks in like grade school or something like that? That works as an idea of how these things are shaped. But really, it'd be more accurate if you built your model out of marshmallows and springs instead of toothpicks. But that gets really hard to do because then everything's wobbling all the time, right? Turns out that's the way molecules actually behave. They don't have like fixed shapes. They have average shapes where everything's kind of always shifting back and forth a little bit. All right, so what does this look like in practice? How do we actually draw this? If I'm not gonna ask you to draw that graph every time. We basically just look at these atoms and we look at how many empty spots they have. How many vacancies do they have in that valence shell? However many vacancies they have, that's how many bonds they need to form in order to be stable. Because every time we form a bond, so for between these two fluorines, those two electrons count for both fluorines' valence. The fluorine already had 7 electrons, it had 1 vacancy. So it needs to make 1 bond. And that's going to give us a molecule of fluorine.
When we were doing the ionic compounds, I was kind of assuming that's how they were bonding together. But is there a difference between how ionic compounds combine?
So ionic compounds are more, it's more that it's the opposite charges. And really we describe these like they're two different things, but it turns out that ionic bonds are really an extreme case of covalent bonds. So you're not wrong to think of it that way.
It's more their attraction, but
It's more about their attraction. So one of the things that's different about covalent bonds versus ionic bonds, and I kind of glossed over it, I actually had it on an earlier slide, is that when you put ionic compounds and you dissolve them in water, you actually separate the ions from each other. When you take a salt crystal and you put it in water, the water actually basically surrounds each of those ions and pulls them apart from each other. So you actually get the ions individually in that case.
they're still of the compound that was made.
Kind of. So if we start with NaCl solid, when we dissolve it in water, we get sodium ions floating around. We call it aqueous state, and we get chlorides floating around. If we remove the water, they go back to being this, sticking together, but when they're dissolved, they separate out. And so it's more like the solid that's just being held together because positives are attracted to negatives, and we can overcome that if we surround them with water.
Okay.
But molecules, like sugar, when you dissolve sugar in water, because it's covalent compounds, if you actually separated those things apart, nothing would have a full valence anymore, and everything would be super unstable. So molecular compounds, covalent compounds, stay all as one piece when you dissolve them in water. But ionic compounds actually split up into their individual ions. That's probably the biggest difference between the two. Is how easy it is to separate the ions, because sodium with the plus charge has a full valence, right? Chloride with the negative charge has a full valence, so they're both relatively stable. We try to do the same thing with this fluorine. We pull it apart, we get 2 incomplete valences, so it doesn't split apart that way.
Thank you.
No problem. All right, so what this means is that once again, our periodic table is going to be our guiding light, our North Star. Periodic table tells us how many bonds everything's going to make, because the periodic table tells us how many valence electrons and how many vacancies everything has. So when we're counting valence electrons, we were counting from the left-hand side. We counted over till we got to our element, right? We're counting vacancies, we're counting how many steps does it take to get to the right-hand side. So oxygen, it takes 2 steps to get from oxygen to neon. So oxygen's got 2 vacancies. So it's the same logic for what's the stable charge for oxide. But if we're not talking about actually giving oxygen the electrons, we're talking about oxygen sharing the electrons. Instead of talking about how many electrons does it need to gain, we're talking about how many bonds does it need to form. It's the same logic, it's just that oxygen doesn't get to keep the electrons to itself. It's forced to share them with the other atoms in the system. All right. Trying to decide order to do this next. We'll do this part. So this idea of representing the electrons as dots leads to what's called a Lewis dot structure. And a Lewis dot structure is basically a drawing that allows us to see how many bonds things need to form and how we're going to arrange these electrons so that everything gets to be stable. So our number one goal with the Lewis dot structure is arrange your electrons so that everything has a full valence. That's our goal for each of these. Right? But there's basically there's a set of criteria that we're going to follow in order to do this. Right? So this is for a molecule called methane, which is CH4. The way we do these Lewis dot structures is our number one rule is going to be use the right number of electrons. Excuse me. We have to use the right number of valence electrons because we can't make matter out of nothing. Right? We're not able to do that at this point. You have to talk to the theoretical physicists about that. Turns out we, as a species, can, in small amounts, make matter from nothing with an extreme amount of energy, but not in this class yet. So we need the right number of electrons. So how many valence electrons do we have from carbon? How many valence electrons does carbon have? So we have 4 electrons from the carbon. And then we have 4 hydrogens. Each hydrogen gets to bring its valence electrons too. But how many electrons does hydrogen have? So that gives us a total of 8 valence electrons. And I'm very specifically going to remind you, now we're not counting all of our electrons, we're counting valence electrons only. Right, those core electrons, like carbon has a 1s2, right? That first energy level, those 1s electrons are never going to react with anything else. They're too stable already. So we're only talking about valence shell. So if we have 8 electrons total, our next criteria is everything has a full valence. If we can say yes to these 2 criteria, then we drew our Lewis dot structure properly. Turns out there's one more we'll get to in a little bit that determines if you drew the best possible Lewis dot structure. But for now, if you can say yes to these 2 criteria, then it is a good Lewis dot structure. It might not be the best one though. So what we're going to do is if we need to share electrons, and this is all one molecule, we have to choose something to go in the middle. Because if something is going to form bonds and be surrounded by all these other electrons to become more stable, we have to choose something to put in the middle that's going to share with everything around it. So out of these 2, carbon versus hydrogen, which one can make the most bonds? Carbon. Yeah, carbon has 4 vacancies, hydrogen only has 1 vacancy, right? So carbon's going to go in the middle. We're just going to surround it with hydrogens. We've got 4 hydrogens, we draw 4 H's around our carbon. The next step is just, okay, if we have 8 electrons, how can we arrange the electrons so that everything is stable? And in this case, we know that there's 4 hydrogens around a central carbon. We're just going to start by saying, okay, let's connect everything. Every one of these bonds represents 2 electrons. And so it's one line, but the other way we could draw it, the other way it was drawn on the other slide was represent each of these as a pair of dots. If each of those dots represents an electron, how many electrons did we use? Not a trick question, it's as simple as how many dots are there? 8. How many electrons did we have to work with? We used all of our electrons. Boom, criterion one is satisfied. Did we fill everything's valence?
Yes.
Yeah, carbon's got 8 electrons in its valence shell. Each hydrogen has 2 electrons in its valence shell. Everything's satisfied. Criterion 2, satisfied. Right, so every time we're going to draw a Lewis dot structure, it goes the same way. Count your electrons, figure out what goes in the middle, put everything else around what goes in the middle, and start filling in electrons until everything has a full valence. Right? The order, you can count your total number of valence electrons whenever you want. I usually do it at the beginning, but for some reason when I wrote this slide, I put it as step 3. Doesn't really matter. Right, because we didn't start using the electrons until after we did these other steps anyway, right? So put your atom with the most bonds in the middle, surround it with everything else, start putting electrons down. So let's do water. H2O. How many electrons do we have to work with? So each hydrogen brings 1 electron. Then how many does the oxygen have? 6. 6 electrons from the oxygen, 2 from the hydrogens. Once again, we have 8 electrons to work with. Between hydrogen and oxygen, what can form the most bonds?
Oxygen.
Oxygen. So we put oxygen in the middle. Put the hydrogens around it. We have 8 electrons to work with. Where should we start distributing the electrons?
H's.
We know those hydrogens have to be attached, so let's draw some bonds there. How many electrons did we just use?
4.
4. So remember that each of the bonds is 2 electrons. So we used 4 electrons, which means we got 4 electrons left.
Like do 2 lines.
So we could do that, but does hydrogen want to have that many electrons? You never know. Check your periodic table. Hydrogen's in the first row, right? Which means it only needs 2 electrons to fill its valence. So I'm glad you said that though, because this brings up one of the cardinal sins of chemistry. You never give something more electrons than it can handle. Hydrogen can only take 2 electrons. So it will never have more than 2 electrons around a hydrogen. Anything in the second row of the periodic table will never have more than 8 electrons in its valence. That's a hard rule. And you know I don't use absolutes very often, but I will say never draw more than 8 electrons around something in row 2. Never draw more than 2 electrons to a hydrogen. So we're not doing that. We have 4 electrons left. Where can we put them? Yeah, we don't usually draw them as a line if it's not a bond. So we wouldn't draw it like that to nothing. But on the other hand, it gets really easy to miss 2 little dots if you draw it like that. So these are what are called lone pairs or non-bonding pairs. you have non-bonding pairs, I usually do that so that you don't forget that they're there. Otherwise, it's really easy to miss that you already put two dots there. Looks a little, it's like balloon shaped. It turns out these orbitals, these non-bonding pairs are shaped kind of like a party balloon. So we kind of give it that sort of rounded shape. So now have we used, that's all of our electrons, right? So criterion 1, set. Use eight electrons total, we're good there. Did we fill all the valences? Are the hydrogens satisfied? Yeah. Is oxygen satisfied? Yeah. So this is our Lewis dot structure for water. They might have more electrons, and we're gonna fine tune this a little bit more with more practice. But that's the heart of Lewis dot structures, is figure out how many electrons you have and then fill all the valences with the electrons you have. Never use more electrons than you have. If you have electrons, you have to use them somewhere. That's the first criterion, is always use the right number of electrons. The second criterion is always fill all the valences. So here's another way of drawing it. I drew my hydrogens on opposite sides from each other. But this slide has them 90 degrees from each other. Does that make a difference? In both cases, I filled all my valences and I used 8 electrons. It turns out one of the things you have to remember about these molecules is that they're three-dimensional objects. We're drawing them flat on a piece of paper, but they actually exist in 3 dimensions. So this actually isn't shaped where everything is 90 degrees from each other. This actually has a shape called a tetrahedral shape, where all of these clouds of electrons are 109 degrees from each other. How does that work? Because it's only 360 degrees around. It works because we're in 3 dimensions. That's what that lab for next week that's going to be on your computer that I was talking about, visualizing things in 3D, has to do with what does this actually look like in 3 dimensions? Because even that carbon example, we drew this one's a little bit easier to draw the shape of. We drew it like this, where all of our bonds were 90 degrees from each other, just because it's flat on a piece of paper. So it's easiest to draw things 90 degrees from each other. But when you actually look at this molecule, you get something that's shaped did not leave myself enough room. Like this. Which, what the heck am I doing drawing it like this? This wedge is supposed to represent that this hydrogen is sticking out of the board towards you. It's a really crude way of showing perspective. It's like, it's got this straight line as a bond, except it's pointed this way, so this end of the bond is getting bigger as it's pointing towards you. And this dotted line, if I was more careful with it, it's supposed to be a wedge. It's getting smaller as it's going into the board away from us. So basically, when we start incorporating 3 dimensions, we have to start being able to visualize things in 3 dimensions, because this molecule actually looks like this, not 90 degrees. All right. When we don't have enough electrons, last thing, then we'll be done for the day. If we don't have enough electrons to do it our normal way, sometimes we have to actually make atoms share more than normal. So look at CO2, carbon dioxide. How many valence electrons does CO2 have? We get 4 electrons from the carbon. Then there's 2 oxygens, each oxygen has 6 electrons, valence electrons, right? So 12 plus 4 is 16. What can form more bonds, carbon or oxygen? Carbon, so carbon goes in the middle. Oxygen on either side. Start by drawing our bonds between the carbons and oxygens. We've just used 4 electrons, right? So 12 electrons left. How many electrons does each oxygen still need to get to a full valence? 2? We're trying to get to 8 for oxygen, right? It's got 2. It needs to get to 8, so it needs, each oxygen needs 6 more electrons. Now how many electrons do I have left? I just used another 12 electrons, right? No electrons left. So I used the right number of electrons. That was our first criterion. That's the number one thing we're looking at. Did I fill all the valences? No, the oxygens are both stable, but the carbon only has 4 valence electrons and it needs to get to 8. So when this happens, we've run out of electrons, but we still haven't filled all the valences. This is when we start making double bonds, like we tried to do earlier. Right, so basically what we do when we run out of electrons is those atoms that are already stable, we're going to take some of their non-bonding electrons and turn them into bonds. So we're going to take this oxygen, we're going to take away 2 electrons and turn it into another bond. Now is the carbon satisfied? No, this oxygen is still good though, because it still has 8 electrons, but the carbon still it's sitting at 6. It needs 2 more. So we're just going to do that one more time. Erase one of the non-bonding pairs you already drew. And turn it into a bond. Now everything's satisfied, right? I still only used a total of 16 electrons, but all of my oxygens have 8 and my carbon has 8. Everything's satisfied, has a full valence. And so the only time you're going to make double bonds or triple bonds is when you run out of electrons before everything has a full valence. And usually it's going to be easiest to see how this works if you start at the outside, fill up the atoms at the outside, and then see what's left over. Right, so you work from the outside in with these Lewis style structures usually. Questions? I'm not going to throw you into the deep end and have you start doing this on your own right away. We're going to do more practice with this. Don't worry. I'll see half of you for lab, in an hour. Then everybody else will see you on Wednesday.
Thank you.